Okay, welcome back. This is going to be one long lecture where our goal is to introduce and understand, well, actually convert our attention to the vector potential and the scalar potential for the electromagnetic field, which when combined will give us the for potential, which can be expressed either covariantly or contravariantly, and ultimately these will allow us to write the electromagnetic field tensor, of course, either covariantly or contravariantly. And the idea here is that we want to start thinking about electromagnetism in this regime. We want to escape thinking about it in this regime to the extent that we separate space with time. And we certainly want to get away from thinking of the fundamental fields as being the magnetic field and the electric field. So the goal of this is to kind of lean into this, get to the point where we understand the development of the electromagnetic field tensor, and our foundational principles will no longer be the Lorentz Force Law. Right? We want to escape where this becomes our starting point. In other words, this is the equation of motion essentially for a charged particle. We don't want to begin with the equation of motion. We want to begin with the principle of least action and use that to generate the equations of motion. Right? We want to use this is the approach we need to settle in on as our fundamental approach as we approach the study of quantum electrodynamics. So that is the goal. So we're going to do this in two different ways. We're going to use two different approaches to get to the definition of the for potential and the Lagrangian for the electromagnetic field. And then we're going to do an analysis probably in the next lecture to get at the electromagnetic field tensor. So let's begin. So the first approach we're going to take is we're going to start with a phenomenological understanding of the answer, right? We are going to use the Lorentz Force Law as a guide to ask us what kind of term do we need to add into the Lagrangian to create an action that will give us this force law, right? So we're sort of starting with the answer, and we're asking what is the term in the Lagrangian we need to get the right answer. So this is a bit backwards, and we will liberate ourselves from this backwards approach in our next approach. But I think this is pretty edifying to begin with because we get to look at, okay, there's this potential piece in the Lagrangian, and it's going to basically be a velocity-dependent potential, right? The potential can be a function of position and a function of velocity, and it can be an explicit function of time as well. But ultimately, we're going to get rid of the explicit function of time, but the velocity and position is still a thing that has to live in the potential. And we know that the force has to be proportional to this thing called electric charge, and it has to be totally proportional to electric charge, and it has to be linear in the velocity, right? Because that's what the Lorentz Force Law tells us. So we're going to design a potential that is the same. It is proportional to charge and linear in velocity, right? So we will, and we know that ultimately this is the equation of motion given by whatever Lagrangian we choose. After we figure out what u is, we're going to have an equation of motion. And by the way, this is where the principle of least action happens, right? Once we've chosen the Lagrangian, once we write down this equation of motion, that is the application of the principle of least action, because this Euler-Lagrange equation came from the variation of the action, which was the time integral of this Lagrangian. So at this point, we have engaged the principle of least action. And if we do this engagement, we know that this potential, whatever we choose for it, is going to show up in exactly this form. The first part of it, the free part of the Lagrangian, is going to give us something that looks like a force, a mass times an acceleration. And this part of the Lagrangian is the part that we're trying to tease out. But tease out isn't very hard if you think of, well, what we're going to do is we're going to guess u, we're going to guess this velocity-dependent potential and see if we can, and then once we guess it, we can calculate all these derivatives. It's going to be a function of r dot and r, so these derivatives are going to be easy. And this time derivative, likewise, it should be simple to do. This front end piece is the same equation of motion applied to this free piece of the Lagrangian. Now, the free piece of the Lagrangian we've already kind of discovered for a relativistic particle, right, was given by this expression here, the rest mass c squared, and this piece here is actually 1 over gamma, right? I frequently mess up these gammas and 1 over gammas. It's just something I've always done, and I'm still doing it. I don't know why. But if you run the Euler-Lagrange equation for that, and I should erase this here, this should be the free part of the Lagrangian in here. And if you take this derivative with respect to r dot, right, you end up with this large expression. But this guy here, I mean, obviously, the square root goes into the denominator. Then you take the derivative of this part, and you get 2r dot 1 over c squared. The c squareds cancel. This is gamma, and you end up with gamma m0 r dot as your as this expression. And that is what ultimately lands, I guess. Let's see. Ultimately, if you choose the relativistic Lagrangian, that means a gamma will land right there. But if you choose a non-relativistic Lagrangian, then this just becomes mr dot. So you kind of have that choice. We're obviously working relativistically, but understand the difference is only this gamma. So then we have this to calculate. So what is our guess? Well, our guess is something that's proportional to charge, which is what this whole expression is. Charge, multiply everything by charge, and it's proportional to charge. And it's going to have it's got to be a scalar. And if the whole thing's proportional to charge, but it only has to be linear in velocity, well, that means there should be a scalar part that's not affected by the velocity, and then this part that's linear in velocity. And there you have it. But you have to turn the velocity, which is a vector, into a scalar. So we need to dot it into some sort of vector. Now, we don't know anything about this vector, but we do know that when the velocity is dotted into it, we get a scalar. Multiplied by e means it's proportional to charge, but it's linear in velocity. And then you have this part that's scalar proportional to charge. So this is our guess. This is our guess. The guess constitutes some scalar part and some vector part. And they're both functions of position and time. So this vector is a vector field, which is a function of position and time. And this is a scalar field as a function of position and time. So this guy here, I mean, to be clear, you know, if space-time is mapped out by some coordinate system at every point in space-time, there will be established some vector that has 3 components. And that vector will be C1, C1 of the coordinate and the time, C2 coordinate time, C3 coordinate time, right? It's a vector that lives, and there's another vector here that's different, and there's another vector here that's different. And that difference is the difference in these components as a function of space as laid out by this little grid, and the grid is the coordinate system. Now, likewise, this guy is a bit different. This guy, at every point, there's a different value, a big value, a medium value, a little value, could be 0, but it's a scalar quantity at every point in time, at every point in space and time. So this is a vector field, this is a scalar field. Just got to start re-emphasizing what these fields mean, because that's what we want to study ultimately, is field theory, right? So now we can calculate this force F. Now, why are we calling this a force, right? Because what we're doing is we're just running the Euler-Lagrange equation. We're running this equation right here, right? You replace u in this equation with this guy, and you end up with this expression right here. And you'll notice I've already broken this vector into C1, C2, and C3. And notice how I'm not using contravariant or covariant notation, right? These are just the one component, two component, and three component, X, Y, and Z. And this dot product is V1, C1, V2, C2, V3, C3, which you're happy to think of as Vx, Cx, Vy, Cy, and Vz, Cz, if you wish. But the idea is that we're writing this down as a force, and that comes back to this expression here, right? This guy is a force, so if I swing this to the other side of the expression, we should get a force, right? So that's what this is. This is a force. And that's, of course, what we're after, right? Because we're trying to check our Lorentz Force Law against this guess for the Lagrangian that represents what we hope to be the interaction of a particle with a certain charge and a certain velocity with a field. And so now when we write this Lagrangian down, notice that r dot here is a scalar, but r dot is a velocity. And the way the notation goes, the way we're going to use the notation is we're going to write partial d by v vector, right? So first of all, r dot, right, we're going to write as just v. So that's the first thing to understand. But what the heck is a partial derivative with respect to a vector? And all that is meant to mean it's shorthand notation. And I'm putting it in here because this is the kind of shorthand notation you will see out there and you want to get used to. But what this shorthand notation means is we're taking the partial derivative of this entire thing with respect to each of the components of v and then just adding it up, right? So what we're doing is we're compressing three equations into one using vector notation. So this piece here, this first part of this partial derivative with respect to this v vector, is the partial derivative of all three of these things with respect to v1, with respect to v2, with respect to v3, and then it's applied in the direction of v1, the direction of v2, and the direction of v3. So it's very similar to a gradient. And the derivative of this with respect to v1, well, that term has no dependence on v1, and that term has no dependence on v1, because remember, c is dependent only on r, right? Only on position. So the only velocity dependence in this entire sum is the v1, v2, and v3 itself. So only the partial derivative v1, c1 with respect to v1 survives, and that'll be given a v1 hat direction. And likewise, v2, c2, it only survives the partial derivative with respect to v2, and v3, c3 only survives the partial derivative with respect to v3. And we give it this direction because we're taking this derivative with respect to a vector. So it's a bit of a shorthand, right? This is going to break up into three independent component equations that are going to be the same as the three Lagrange equations that matter. So that's how we understand this piece right here. That's how we understand this derivative. The way using this notation is used in Landau and Lifshitz, the book, a very famous book that I will reference a lot at the latter part of this lecture. This is a book. Ultimately, your goal should be to be comfortable with the notation in this book. It's difficult, though. It's not easy, and it's certainly not for beginners. But on the other hand, if it's explained, it's not that hard either. So what remains then is to take the time derivative of this. We'll do that in a moment. But then we now need this spatial derivative part. And the spatial derivative part of the function u, right? This the function u will be the spatial derivative part of the scalar field and the spatial derivative part of this dot product of v and the vector field. The scalar field is easy. It's just going to be E with the spatial derivative of phi. Now this is again the same thing. We're taking it with respect to a vector, right? So we got to be a little careful about that. But when we take the derivative with respect to the vector of the spatial part, it's just this guy right here, d phi dr1 in the r1 direction, d phi dr2 in the r2 direction, d phi dr3 in the r3 direction. This is the definition. When I write the partial derivative of something with respect to a vector, I basically mean the partial derivative with respect to each of the components, and then you add a vector in the direction of the component, right? You're going to see in a moment that this is literally the gradient, right? That's the definition of the gradient, and that's exactly what this is. And then we need to take the partial derivative with respect to the position vector r of v dot c. And that's a little trickier because v dot c, first of all, is v1, c1, v2, c2, v3, c3. And we're taking the partial derivative with respect to r of each of these expressions. But that is the way this is blown up, and we have to kind of work on this and work on this. And what we end up with is this guy here. Each of these partial derivatives is trivial, right? The partial derivative of v1 c1 with respect to v1 is just c1. The partial derivative of v2 c2 with respect to v2 is just c2. And likewise here, the result is just c3. So this ends up, because remember, there's no velocity dependence in c itself. And the reason there's no velocity dependence in c itself is because, remember, we're forcing u to be proportional in velocity, right? And if c was velocity dependent, then if you change the velocity, you would get a proportional to velocity change, but then you'd get some other unknown change involving whatever happens to c. So c is not dependent on velocity, which is important. But given that, these guys all go away, and you just end up with c1 in the v1 direction, c2 in the v2 direction, and c3 in the v3 direction. But v1, v2, and v3 are just, these unit vectors are just x, y, and z, or x1, r1, z1 unit direction. So this becomes just the vector c. Everything in here just simplifies, all of this stuff just simplifies to the vector c. How convenient, right? And now we're just asking, what's the time derivative of this vector c that we've invented for the purpose of creating our Lagrangian? And then this part, this is literally just, actually, these little, so you see what I did here? I wrote partial derivative with respect to the vector r. And then here I wrote r1, r2, r3, but I have these guys as vectors also. That's actually not right, right? These guys are just the actual directions, right? In fact, why don't I erase this just to make it really clear? This is x1, x2, and x3, the spatial directions, right? So that's a lot easier to understand. And by the way, the whole point is that this is obvious. Oops, then if I do that, I should change these to x1 hat, x2 hat, x3 hat, the unit vectors in those directions. And now I get what I want, which is that this is literally the definition of the gradient, right? That's literally what that means. And that leaves us with this last term where we still want, what do we want? We want this is the gradient, right? This is basically the gradient. We want the gradient of whatever this is. And these guys are functions of position and time. So, but the velocities, remember the velocities, r dot equals v, right? So the velocities are actually, those are independent variables in our system, right? The two independent variables are position and velocity. So these are independent variables. So these guys are not subject to change when you change x, y, and z. So they come out, right? They come out. But then each of these guys is in fact getting we're taking the gradient of each of these guys. So this now becomes the sum over j of Vj times the gradient of the components, right? This is the gradient of each component. And that's totally different than the gradient of just a regular scalar function. Well, it is the gradient of a scalar function, but the scalar function, this is a scalar function because it is a component, right? So C as a vector is a scalar function of r and t x hat plus a scalar function of r and t y hat and z hat too. The vector part is in these unit vectors, but that is a scalar. So you can take the gradient of C1, no problem. So this becomes the expression that compresses this last term into something we can work with. So now this guy is our force, and we know that it's equal to E V cross B over C. So we can put E plus, we can put the Lorentz force on this side, and we can put the work we've done on the right side. And we can now start crunching. I actually looking ahead, I'd like to write it in a more index-driven form than in this Vj with gradient Cj. I'm going to write it in this form here. And so this is now a double sum, and it's a sum where the velocity is summed into the component, and then the position or the derivative is actually summed into the unit vector. So let's make sure we understand how to do it, because this sum is going to drive our final answer significantly. So let's look at this. Let's blow this guy up. We're going to blow up this guy. So we're going to have a look at this derivative. Now, right now I'm writing the vector r is going to be R1, R2, and R3, right? Which you can also think of as X, Y, and Z, or you can think of as X1, X2, X3, however you'd like to do it, right? I'm just going to stick with these R's for right now. I guess over here, the substitution I made was with X, right? So I'm totally mixing up my notations here. But I wanted to do it with X1, X2, X3 because I felt like this screamed gradient a bit more. But this is really just notation, right? And anybody who's been following my lectures know that I am not a stickler for sticking through with consistent notation from beginning to end. Anyway, because I like notation is what this is kind of all about. I love experimenting with it and feeling it out and kind of deciding, like, if I were to write a book, what notation would I use? If I would write this in a book, I would definitely stick to one notation. But you can think of this as just X1, X2, X3. We're not using superscript, subscript, relativistic, Lorentz invariant notation for any of this right now, right? For example, here I imply this is a sum. I've thrown the sum in here. I'm not even implying an Einstein sum. And even if I was, I would have to use subscripts and superscripts to be strict to the Einstein convention. But there is definitely a convention where this is gone, right? And you just assume the sum when you see any repeated index. But we're not. I'm trying not to use that convention. I'm using this more strict elementary linear algebra convention where they stick in the sum. Even here, right? I've got this double sum. But let's see how we can get from here to this double sum really clearly. If you blow this up, as I said before, this is essentially the gradient, right? So it's the derivative with respect to the first coordinate of each of these terms and get in the vector direction of the coordinates. So it's the derivative with respect to R1 of V1, C1 in the R1 direction, the derivative with respect to R2 of V2, C2 in the R1 direction, and derivative of respect with R1 of V3, C3 in R direction. It's all with respect to R1. I think I said R2 here for a second. And then
you change this to R2 and you do the same thing. Now, obviously, I've organized this so that the first execution of this gradient derivative with respect to R1 is now in a column, and then with respect to R2 is in this column, and with respect to R3 is in this column. The reason I did that is because the sum that I want to create out of this is going to be a sum. We're first going to sort of establish we want to add up all of the vector components with respect to R1, and we can kind of see that that will be V1, C1, V2, C2, V3, C3. So there's a sum over one index on V1, on V and C, and then a sum over a separate index on R. And that's what we have here, right? This sum over Rj is going to capture the derivative and the unit vector. And then this sum over I is going to capture the V1, C1, V2, C2, V3, C3. And so summing over I, you should get the same index value for V and C. And then summing over J, you get the same index value for Rj and Rj unit vector. And so this double sum captures this result. And notice it is a vector, right? This thing is a vector because you have this unit vector over here. Now, if you were really to get fancy, you can turn this into this expression. This is a little bit weird because you have the gradient of a vector, right? And that actually is a tensor. So when you have a tensor and you're dotting a tensor into, or you're dotting a vector into a tensor, you get a vector out. I don't want to go into this right now, but it is some understanding that this guy here, it's a two-index object, right? This guy is actually a tensor. So interesting enough, but we don't need to get into that particularly. We just need to have this form for now. So that form is what I'm going to put right here. Okay. So now I have the Lorentz Force Law, which is our phenomenological fact derived from experiments. Notice, by the way, it's Gaussian units. I think I may have mentioned this before, but you know, units of electric and magnetic field are the same in these units. And then I have the time derivative of a vector field. This is called a stream derivative. We'll be studying that in detail in a moment. And then we have the gradient of the potential, and we have this term that we kind of squeezed out of this final expression, which came from the gradient of this function. This is a function on the spacetime, right? V dot C, that's a regular vector. That's a regular vector. That's a dot product. The result should be a scalar. That's a scalar function. So this is really the gradient of a scalar function. But by the time we sort of peeled it apart, we end up with this expression. Notice E is gone because this was proportional to E, and this is all proportional to E, so E just drops out. Okay, so now we're going to study this guy. All right, so let's see. I rewrote it up here, so let's have a look here. This is my shorthand notation. You know what? Let me clean this up to make it consistent. There, I took this out, which was that more advanced way of looking at it, and I replaced it with just the literal index summation expression. But we're going to study this guy. So this guy's called the stream derivative. Notice it's a total derivative of a vector, right? So the definition of such a thing is essentially it's driven by the chain rule, right? But it's the partial derivative of each component of the vector with respect to time. So it's the partial derivative of the vector with respect to time explicitly. And then it's the partial derivative of the vector with respect to every independent variable, which is, in this case, R1, R2, and R3, each and then multiplied by that variable's time dependence, the partial derivative of that variable's time dependence. And notice this is still a vector in here, right? So this is, this is going to be, there's going to be three components to each of these derivatives for this total derivative. And so these guys can be compressed into a single expression, partial derivative of the vector field with respect to time, times the sum over j of the partial derivative of the vector field with respect to each component direction multiplied by the velocity, because this guy here, dr1 dt, that's v1, right? This guy here, well, that's v2, and this guy here, well, that's v3. So summing over 1, 2, and 3 captures each of those partial derivatives. And then this cat here is just summing over, well, let's do it out explicitly, right? This expression here, if you were to blow it up again a little more cleanly, well, now that we have this, we blow it up again. We get the partial derivative of c1 with respect to time in the r1 direction, c2 with respect to time in the r2 direction, and c3 with respect to time in the r3 direction. That is this. That's what this guy here means. The partial derivative of the vector field with respect to time, we can blow it up into 3 coordinates, right? See this 3 components. And each of these C subscripts is one of the 3 components. And then this last part, it's already a sum over J, but this is a vector too. So we'll do it component by component. So we add in an additional summation, just like we did a moment ago. And now we have the partial derivative of CI. We sum over each of the components of C for this purpose. We're now summing over each of the components of C. There's already a sum over the components of J, so this becomes a double sum, and that turns this vector into a component expression, and now all the vector nature lives in this unit vector here, right? So this expression here just becomes this double sum. Now notice, this is not the same as this, right? Let me see if I'll blow those two up. The velocity is being summed in conjunction with the component of the field C. And in this case, the velocity is being summed over the direction of the partial derivative. And it's the field C that's being summed with the unit vector. And here, it's the component of the derivative that's being summed with the unit vector. So this and this look very similar, but they're not the same. They're not the same at all. But we now combine everything together, meaning we now, what is everything? Well, we're taking the stream derivative. The first part of the stream derivative gives us this whole vector piece here, which I'm recompressing just so you can see what it is, right? In other words, I blew it up here so it was absolutely clear what this term meant. But now I'm going to recompress it because I don't want to write out all 3 terms. So this is the first piece that flows. The second piece that flows is, well, this guy obviously just drops right in there without any modification, right? So we have this gradient of the field. And then, let's see, the next part is the part of the stream derivative, this part of the stream derivative that is this much weightier part, which becomes this summation, which becomes this double sum, right? That lands, let's see, this is the one where velocity is got the same index as r. So that's this piece right here, right? So this part, the stream derivative broke into one part already, but the second part flows from here into our final expression as a double sum, as a part of a double sum. And that double sum lands right here. And then ultimately, this double sum, which came to us from this piece over here, which came to us from this piece of the force Lagrangian, right? So these 2 pieces combine to form this piece, which came all the way over to here, and then that just flows directly down to here, right? And it's the double sum is right there, right? So now we've combined everything into one expression here. So this is the expression we now have to tease apart. So now I go to Wikipedia and I look at my cross product rule section, and what I'm taking note of is this and this, right? These sums have the exact same structure as the two pieces that live inside our double sum, right? So we have, if you replace the vector A with V and the vector B with C, you realize that this form where the velocity is summed along with the derivative is exactly the same as this form here, right? Where the A is summed into the derivative. So this should be, so this sum can be replaced with A dot del acting on B, which is V dot del acting on C in our case. So this becomes V dot del acting on C. That's what this whole summation, including this vector piece, can be replaced with. And then this guy here, likewise, this is now the velocity summed into the vector field C, again replacing A with V and B with C, you get this structure here, right, where A is being summed in with B, and this structure is the same as A dot del B. Now, del B, remember, this is the gradient of a vector field. This looks like it should be some kind of scalar, right? But it's not, because this is a tensor, right? So this is like the most tricky versions of these vector calculus identities, because you don't see del vector field or gradient vector field very often, but it's a tensor. So A dot gradient vector field is actually a vector. Now this doesn't look like a vector, but if you look at it closely, you realize you're summing over I. They're implying the sum over I. See, they're missing the sum over I here because they are implying it. But what they're also missing is the sum over J with X J hat, right? Right, that they're missing that too. So this is a vector, right? That's very important. So likewise over here, right? They're missing this ij sum and xj hat, right? So once you do that, you can now replace this whole structure here with these two expressions here. And the reason that's important is only because we're using this as a bit of a crutch, right? Meaning I'm using this vector identity table right out of Wikipedia as a crutch because I want to get from these summations into these vectors because I want to realize that this vector identity right here, let's see, I will circle it. This vector identity right here is operating in our problem, right? We've got v dot del on C minus v dot del on C minus v dot del on C. They've got a dot del on B minus a dot del on B. So they've got the opposite, right? But the opposite of that equals A cross del cross B. And that's what we want to exploit. So what we realize pretty quickly is that we flip this sign, switch these two, flip this sign, and we end up with V cross del cross C by utilizing this identity here, right? This identity, right? This becomes V cross del cross C equals V dot del C minus V dot del V dot del C, like this. And so we just pick up a minus sign. And that leaves us with this expression right here, which is what we're after. And so this expression is our goal because now we can equate the left side with the right side piece by piece, right? If the left side is true and the right side is true, Well, the left side we know is true from experimental observations. The right side is sort of a guess, right? But if our guess was good, right, meaning if the u r dot we chose was legit, then then for sure these two should be the same, right? But the only way these can be the same is if b is equal to some is proportional to del cross c, so that this term here equals this term here, right? This is the only term proportional to v. So all the proportionality of v lives in b over here, and all the proportionality to v lives in del cross c over here. So in order for this to be the case, if I define A, the vector field A, as minus the speed of light times this vector field C, right, then this should work out, right? Because if I replace C with A, I have to add a 1 over C, right? I have to go 1 over C. I have to change the minus to a plus, and then the C can become an A. And now I have V cross a vector over C, which is what this is, V cross a vector over C. So now I just have to make the identity that B equals del cross A, right? So now I know that this vector field B is the curl of some other vector field A, right? But if the vector field B is the curl of vector field A, then I know by my vector calculus rules that that the divergence of B must equal 0, because the divergence of a curl is always 0. I know this is true for Maxwell's equations. So you could look at it two ways. I could say, well, I studied physics and I know the force law. I went through this, and if my U is true, then this magnetic field V is the curl of some vector potential. But if that's true, then it should also be true that if I study this magnetic field closely, I should discover its divergence is always 0. That would be a way of checking whether U is true. Or you could also say, no, not only do I know the physics of motion of a particle in an electromagnetic field, I also know Maxwell's equations. I know this is true. And what I've done is I've now found further evidence to believe that U is correct the way I've written it. Because not only have I discovered the important fact that V is the curl of some vector potential, but it's also consistent with Maxwell's equation. So you can decide whether you want to call this a hypothetical discovery of this, or use this to reinforce your belief about U. But either way, you have to assume something. You either assume U and then you say, I've discovered del cross B equals 0, or you say, I guessed at U and I know del cross B is 0, and U's looking pretty good now. Okay, but either way, this is how we end up defining the vector of potential from relatively first principles, I suppose. I mean, it depends what you want to say you started knowing. So from this, you ended up with, let me clean it up. Okay, so here it is cleaned up. We assert that A is minus the speed of light times our assumed vector field C, and then we write B as del cross A. And then this term here just becomes V over C del cross A. That minus becomes a plus. Now, a lot of times when you go through this, right, this is one of the things I tend to like to do, right, is I started with a very general assumption of a scalar field and a vector field, and I didn't throw in any proportionalities. Very often when you see this work done, they'll start with A here, and they'll start with V over C here, because they know how it's going to end, and they don't want to go through the trouble of making this substitution at the end. I prefer to make that substitution at the end to see how these nice units are defined from the beginning. I feel like if you define things with the nice clean units in the beginning, then you're kind of, it's too much assuming the answer, I guess. I don't know, it's just a preference. Anyway, the point is that this sort of becomes irrelevant now, and we live with this term. And so now we have this del cross A here. But we do know that this C can be replaced with A, right? But it has to be replaced with the partial of A over C partial T, right? But C partial T is just x0, right? So this can become, let me erase this. It becomes the format it ends up looking at is partial A R0. Well, it's really x0. Well, let's just leave it as 1 over C partial T, like that. And then you get minus this gradient field. So you know that the scalar field is still a thing. And plus V over C del cross A. But now you look at this part and you realize that has got to be equal to the electric field, right? The electric field. And there you have it. This is the way you derive the fact that there's a vector potential, that given this assumption, given these assumptions about you, you end up with a vector potential for B, and this time derivative of that vector potential divided by C minus a scalar potential is, oops, I forgot a minus sign. There's a minus sign here, right? There's a minus sign right here, right? And that's what he is. All right, so we've done this from first principles. We've derived our two vector potential expressions from our first principle being the Lorentz Force Law, right? The Lorentz Force Law. Now I'm going to very quickly redo this to a point. I'm not going to redo the entire thing. I'll redo it up to about here, which isn't very far, without that assumption, with a different assumption. And that's the assumption that's used in Landau and Lifshitz. Landau and Lifshitz doesn't make this Lorentz Force Law assumption. They lean entirely on the principle of least action and Lorentz invariance, which very quickly gets you here anyway. So that the principle of least action gets you here, and Lorentz invariance is what they use to invent a field. And Lorentz invariance lands them right here very quickly. And then their assumptions are just Lorentz invariance. A simple proposition for you, Lorentz invariance, and then all of a sudden they've developed what is tantamount to a prediction for what the force law should be. And then they also get the potentials as well. So let's have a quick look at that before we end this video. Well, unfortunately, there is no quick look at this. So we'll begin this in the next lesson, where we'll start with this Lorentz invariant potential and derive the same thing we did. And then at the same time, we'll also discover the electromagnetic field tensor. So we'll dig into the different Landau and Lifshitz analysis in the next lesson. Okay, see you then.